Okay, today I'm going to talk about numerical integration that we mostly used in our calculations.
Right. Need to click inside.
And first of all,
Before going to that, always provide some big picture. So what kind of integration are we doing here?
what type of means, I don't know, like midpoint trapezoidals.
So what are the functions that we're trying to integrate?
We are not sure about like the function, but if area, like we want to find the area of the curve, like if we are not sure about the real formula, then we can approximate some function there and find the area of that and do AD. If there are like infinite area, then we can find the small part of area and then add that to the whole part, and we can find that.
This is a mathematician's way to explain it, which I like. This one part that so not saying this is a best thing, but so when Deepa you're talking to, I think your audience is probably more chemistry people and probably material science people. Let's imagine that you are talking to Dr. Wang, for instance, and she will ask you, why are you teaching us numerical integration? What are you integrating? Can you tell if she asks you this question, what would you tell her?
We are doing like to find the to find the average of our calculation. Yeah.
What one example is you
to plot the file. To find the slope.
You're getting very close.
Coordination.
It turns out to be in Teresa's case, there's another one, motivation, which is nice. Example,
to find the reaction profile.
That's precisely right. So this is the kind of question that, this is the kind of presentation that we should always start. Remember that we're scientists, we're not mathematicians, so we get pretty close. But sometimes we're getting pretty close to mathematicians, but we're still mostly scientists. So when we present, we should think about that. Most of the time, we're talking to scientists. So what do scientists care? Well, they do care about integration, but they are more interested in what exactly the science you're doing. So you should say, we're trying to obtain the free energy profile of a reaction. It turns out to be the polymerization chain growth reaction. And we are using a technique called Blumen ensemble and constraint dynamics, trying to figure out this reaction profile. So now I have the integrand that I can integrate to the reaction profile. So that's why I need numerical integration. So this could be one motivation. Or if in Teresa's case, as she pointed out, that she actually need coordination number of a particular system. By the way, this can be obtained using appropriately normalized radial distribution function that she just showed you. So that's why she immediately pop up coordination number. And we also did numerical integration there. So that's a good motivation. And this is not criticizing. This is just to say.
I just overall explain why.
That's right. Yeah, you're going.
I'm not relating this to my research.
Yeah, always related to your research, and this is generally so for PhD study, you have a little bit more time to explore around, but the good thing to do is try to find out what you're really enthusiastic about, and you want to focus on the direction that you are most passionate about, and hopefully it can be funded. And yeah, so that's how research works inside the US, probably also in Europe. Probably I don't know the other countries, but that's what most I think most places work. Okay, sorry to interrupt you. Please continue.
Yeah. You know that why we do numerical integration now.
That's right.
And then, yeah, we can do this by considering different shape in the curve, like rectangle, trapezoid, parallelogram, and different. Mostly, I'm going to talk about like midpoint rules and trapezoid rules here. Yeah, I'm taking a screenshot.
Yes, fine. That's perfectly fine.
Yeah. Okay.
I'm playing devil's advocate here. So bear with me and so suppose that somebody asks the question in front of the audience, asks the question that why are we limited? Why are we limiting to a certain number of rules? So why do we choose midpoint? Why are we choosing trapezoids? Is there a reason why we're doing this?
It gives more accurate results for our data.
That's right. We know how to
We can-
evaluate. We know how to evaluate the area of the
area of the rectangle area of the trapezoid.
That's
Yeah.
right. Yeah, so that's why we are choosing. So these rules correspond to things that we can evaluate exactly. But we may not be able to evaluate exactly what the function that because we're going to do general integration. We don't know what the function is.
No. We can use like rectangle with trapezoid rule in the shapes or
Yeah, I'll draw this table. This is the curve. Then we want to find the area. So this is 1 point here. Next. This is new point, right? And we need to draw a rectangle here. It should be at the middle, right? And then if we do the R for this, so this is x-axis, and this is y-axis, and we can call it fx function. And if we are looking for this is the height for this rectangle, and for this point, we are going from here to there. Oh, it should be at the middle. Okay. Like this. And if you are here, this. This size should be like maybe symmetrical or maybe asymmetrical, but just we want to find we want to draw the area of rectangles. We want to find this area of these rectangles, this, and after finding this, suppose this is in x0 position, in xn, we have infinite number there, and this is x1, x2, x3. We are starting from integration from A and going to the B. Yes, we can see. Yes. Here, this is our initial step and this is our ending step. First, we find the area of this part. I'm going to do summation of that. Okay, I'll write the formula first. One. This is the summation of this. For this, we need to find this one. What is this? This is the white between. Yeah, no, distance between these two, this. This is the distance. Del x means summation. And how can we find that? We can find that b minus a upon n. B and a are the interval, this one, and the n is sub interval. Sub interval means how many rectangles are there?
like
If
there are 4, let's suppose, then there will be 4.
Yeah,
And will be 4.
Yeah. And it's 4. If we are looking this diagram.
It should be symmetric, like It should
So,
be.
yeah, it should, for this case, it should be symmetric. If it is not symmetric, then we need to look for like Riemann sum. We need to go there.
And I'm really glad that we have this nice discussion from the audience that asked very, very good questions.
In the diagram, there is symmetric.
Yes, so typically, so let's say this, let me see what is the right order of saying this. So let me start by commenting on the numerical integration in general. So numerical integration, you have a few tricks that allows you to have sample functions, function samples. So what is function samples? Thank you. So in Deepa's case, these numbers, she has the first sample, well, x1. I don't know, I'm conflicting with her.
M1,
M1,
M2.
M2, M3, M4. So in practice, for numerical integration, there are two cases. One is you know what the function is, and then you can basically decide where you sample those points. So that's one class. And the other class is that you are provided by the set. You're already provided with the sample. You don't have the freedom to choose where you put the points. So what Deepa is presenting today are correspond to the algorithms that deal with provided samples. So generally speaking, the provided samples can be uniformly spaced or could be irregularly spaced. So the algorithm that Deepa is presenting, the three methods can be used for any spacing. So that's very good, and then I think that was the reason why Deepa was presenting in this way, that the picture in her mind was not regularly spaced.
Yeah, I want to draw regularly spaced, but
That is right, but this is actually the power of some of these integration methods. So that's the practical perspective, and for presentation perspective, generally speaking, you want to stay away from complexity because it's difficult to present. So what I would suggest you to do is present as you have there. Essentially, start with simple uniform spaced results, and you can tell the story much easier. But Deepa is certainly right that this method that she is trying to present here does not rely on a uniformly spaced sample. But the delta x formula that is on the board is certainly a uniform spaced approximation, not approximation, formula.
It's fine if you do not need that picture later. It's here.
It's good to be using the board, because especially when you are doing something a bit more mathematics. It certainly is uniform enough. I probably cannot draw as uniform.
then you can find the lex from here. Then how to find the FMI, and then we need to find, we know x0, x1, x2, x3. Once we know this part, x1, x0, suppose I'm going from 1 to 4. Yeah. suppose this B is 4 and 1 is A and there is number of 4, 3 by 4, it will be like 0.25 maybe. I think
7.
7, Huh?
7.
7, 5. 0.75. Then we need to, this is in 0 state. This is, I got 0.25 there. I forgot that.
So Deepa, when you present, you can always find the simplest example so that you don't need to compute. For instance, you can set B equal to 4 and A equal to 0, so that you have unit spacing.
Okay. 1. Then it will be 1. And then if this is 0, this will be 1, right?
That's right.
And 1 plus 1, 2, 2 plus
3,
3,
4.
4. Like this, we can find x1, x2, x3. And then how to find m1? To find only one. Just x0 plus x1 divided by 2. And then we can find out between suppose 0 plus 1 divided by 2, it will be 0. Oh, 0.5. And then we need to do function of that, like f1. And the function here, and we get suppose 0. I don't know. 375, anything suppose A, we got A there. And once we got this, and we need to apply the summation on that, like summation of our del x is we got 0, no, 1, and then we need to add this 1 into 0.375 plus 1 into suppose this is just to consider 95 for x2 plus 1, and we can find the area of our curve like that.
Right. So you basically compute the
We have to
rectangles.
compute each like each point M1, M2, M3, and
Yeah.
So this is I think this is probably some mathematician wrote it.
Yeah.
So in practice, what you would do is because as you make the rectangle smaller and smaller by increasing the n, because you are integrating a continuous function. So generally speaking, as you use the smaller window, it becomes a constant function. It doesn't really matter where you choose. So in practice, when you do this, it's also called rectangular rule in numerical integration. Now, what happens is you basically are provided by those point values.
And area of rectangle is like length into breadth into height.
That's right.
And if this is your height, this will be your breadth, and this is like similar like the formula.
That's right. And in my mind, what happens here is very simple. So what you are provided are here. And you have the fx1. Let me just do it in a slightly consistent name. So suppose this is my x1. So my data is x1, fx1, fx2, x2, x3, x4, and then fx3, fx4. So in my mind, basically rectangular rule is like this. You have the spacing between these two doesn't necessarily need to be uniform. So this is delta x1, which is x2 minus x1. You do the area for simple-minded. Deepa's picture is actually better in the so this is called mean values theorem in calculus. So it's actually the more elegant way. But as a naive computational scientist, I typically like simplicity more than mathematically rigorous. Well, this is still mathematically rigorous, but my estimated error would be bigger. But basically, what I do is I compute this one by fx1 delta x1, and this one fx2 delta x2.
So it will not be the midpoint rule.
It is not a midpoint rule, but this is essentially something that will converge to the right
Yeah.
answer if you.
Left
Yes, that's
rules,
right.
right rules, midpoint rules, 3 different rules inside their answer.
That's right, and the no, Deepa, you can see, as you can see, this one is an example that even though my version is much much rougher if we were to just compare the figures, it is easier to understand. So when you present to people, the most important thing is that people get your idea. So even though it could be a little bit it probably doesn't seem to be the most intelligent way to say, but you can make things simple, and then as long as the idea is get across very accurately, it's fine. So this is not criticizing because I know coming from a more mathematical perspective, the midpoint rule is certainly much better. But wanted to show you that in terms of presentation, it's important to simplify things, and as long as it becomes easy to understand without losing the main point, it will save you additional effort. Well, so certainly it's important to understand the difference between the more nuanced part.
Then from this, we can find out our approximate value. And then if we apply these rules here, then we can find the exact value and we can compare that. Like we are getting right or
Right. So Deepa, suppose that you have the luxury of having freedom to choose points. When do you say? When would you say the integration value and the midpoint rule will become essentially the same number? And so
let's getting your
so sorry, this is not well asked. So okay, this is not very well asked question. So let me just state what I was saying, because the time is running out. I may have to run, and I want you to at least cover trapezoidal rule. So this is to say that essentially, as you increase the number of points, so that the rectangle becomes smaller and smaller, you'll get to the target value.
Yeah, we can get closer to our exact value.
That's right.
Then the error will be like less.
That's right. And there are other integration rules. I'm not sure if we'll be able to get to Simpson, but I think trapezoidal rule is another one that is very easy to understand, and it contrasts well here. So are you planning to tell a little bit about trapezoidal?
Yes. Trapezoidal rules is also another methods from which we can find the area, approximate area to the integration. For this, we need to draw trapezoid, same like rectangle. We need to take like 2 points here to form the trapezoid. Suppose this is 1. Zero. 1. Straight. We are also have interval to A2, A and B, from A to B, solve interval. Here also N. For trapezoid, we need to look for 2 points. Last time we are looking this shape. It looks like trapezoid. Then we can draw for this also. Oh. This also. This look like trapezoid, and we need to have x0 and x2. These are to height of the trapezoid, and this will be the base. And for this also, del x is same, b minus a right, and now we have different formula to have the area of trapezoid, which is 1/2. Suppose I will do left height plus right height. This one is left, this one is right. If we are considering this, then this will be the, suppose if I do this fx, then this will be fx1, fx2, fx3, and like this fx n and but simply we can represent formula is like fx I minus 1 plus fx I, right? Like if I have I is equal to 1, then this will be fx0, then this will be fx1. You can do that. And this is the area to find no area. I also need to add
Is
the
delta
left,
x. That's right.
and to find the overall area of this curve, we can apply this formula. It's quite simple.
Yes, and it's very interesting because as Deepa's slide says here, you can see that there are actually a factor of 2 for the interior
Because
ones.
it is repeated twice, and like if we are looking for this is repeated single times, first come here. Like if we are looking for this come twice. So those are on the mirrors and then repeated by 2. And those like A and B part are only repeated once. So they are just 1 there. And if other are repeated twice, so because of that there is 2.
That's right, and that was also the reason why I was giving the more naive example before, because the more naive example differs by this by only a factor of 2 on the boundaries. But by using this trapezoidal rule, you remove the boundary points by a factor of 2, and this will actually gets you a much better error estimate. So it is very interesting by how you sum them. So all the numerical integration is about how you sum your samples, and you can actually get convergence with respect to the number of or the spacing in a different way of convergence, and you can converge much faster.
This one is the expanded form of formula that I have written in above. This one is the like overall formula, and the bottom one is the expanded.
That's right. And one more comment before I have to run, and Deepa can continue a little bit if you have a little bit more time, which is this is a trapezoidal rule in open boundary condition. What happens if you have periodic boundary condition? Can you take a guess?
x0 and xn.
You almost did. You almost did.
There will be no there.
Will be 2. Because when you have periodic boundary condition, when A is periodic with B, this one gets summed twice. So it becomes rectangular rule. And the convergence is the convergence is the right trapezoidal convergence, which is very funny. It turns out that we actually have something similar, or I actually encountered something similar in the quantum espresso code, and there was a bug because of the periodic case. So it's pretty funny. Yeah, so I figure it's a good story to tell before I run. Okay, so since I have to meet Dr. Bowson, I have to I have to be punctual. And Any questions before I take off? And well, you're welcome to continue and ask any questions in a later time. Okay, cool. So I'll have to unfortunately leave.
Oh, I have. But I need to ask you about our last calculation. Like it fails on BCBs in the
Okay.
solving.
So let me see if I'll be able to. So if
Yeah,
I
you
succeed, I'll email you.
Okay.
Otherwise, ask me through email.
Okay.
Ask me through email, and if I survive, because there's not a single meeting. It's more than a single meeting. There is a few. But if I don't get back to you by today, email me.
Mhm.
Sure. See you guys. Have a nice day.
Continuing.